Hi, my name is Samir Desai, and in this video, I'm going to teach you how to synthesize ethers via Williamson ether synthesis.
In the last video, we learned one way to make an ether is through the condensation of alcohols. This method creates a balanced ether that looks like this, where both alkyl groups attached to the oxygen are identical. We can also create asymmetrical ethers through Williamson ether synthesis, so the general ether looks like this, with an R prime to indicate both alkyl groups are not necessarily identical. The general mechanism involves an SN2 substitution between two reactants. The first reactant is a metal alkoxide, seen here. This molecule was derived from an alcohol in which a strong base kicked off the hydrogen on the OH, resulting in a negatively charged oxygen which interacts with the positively charged sodium ion. The second reactant is a partially positive primary alkyl halide. The negatively charged oxygen on the alkoxide acts as a nucleophile to attack the positively charged carbon on the alkyl halide, displacing the halide, which is bromine in this case. We are left with an ether that has two different alkyl groups and a salt, the sodium bromide, as a byproduct. Similarly, this mechanism can proceed with the alkyl halide again, but this time reacting with a phenol to produce an unsymmetrical ether with an alkyl and an aryl. The mechanism works the same way. A strong base will deprotonate the hydrogen on the alcohol, resulting in a molecule that looks like this, with a negatively charged oxygen interacting with the positive sodium ion. The nucleophilic phenoxide will then attack the positive carbon on the alkyl bromide. Again, this results in the ether plus a salt byproduct. Let's use this knowledge to predict the ether synthesized in a Williamson ether reaction. Here we have two reactants, so let's draw them out. The first is potassium ethoxide, which is our alkoxide. The second reactant is our alkyl halide, methyl chloride. Drawing the mechanism, the nucleophilic oxygen attacks the partially positive carbon. This kicks off the chlorine. The resulting molecule is the salt byproduct, sodium chloride, and more importantly, our newly synthesized ether with an oxygen bonded to an ethyl on the left and a methyl on the right. The IUPAC name uses the smaller chain as the prefix and the longer chain as the suffix, so it would be methoxyethane. This matches with B. And for our own knowledge, the common name would be the alkyls alphabetically, so it would be written ethyl methyl ether. This concludes our lesson on synthesizing ethers via Williamson synthesis. At this point, you should feel comfortable with both naming and synthesizing ethers.